This beautifully coloured periodic table is because of lots of different groups, lots of different categories on the periodic table. Group number 1 are also known as alkali metals. Group number 2 are the alkali earth metals or alkaline metals. Group 7 are the halogens. And group 8 are the noble gases. The group right on the far right hand side are group 8 or group 0. These are the noble gases. They have a full outer shell. And because they have a full outer shell, they don't want to gain or lose any electrons, which means they are really, really unreactive. And because they are unreactive, they actually have quite a lot of uses. Helium we use in balloons, and they are also used in neon lights, as you can see here in the amazing city of Osaka. Your alkali metals react very violently with water, and this is where you're going to see some flames coming from, some different colours coming from. This is one of the things that we use to make the different colours in fireworks. So the lovely, lovely lilac flame from potassium we can use in fireworks. If you've seen these in school, these are soft grey metals which are easily cuttable. They need to be kept in oil so it doesn't react with oxygen or with the water in the air, because it's a very, very violent reaction. When the metal reacts with oxygen, we're going to get a metal oxide, which if you've seen these in school, when it was cut, it was shiny, but it soon started to dull. The dullness is the metal oxide. The metal plus water is going to form a metal hydroxide. This gives it its name, it's alkaline metal, because the metal hydroxide is going to be alkaline. You can see that by the change in indicator if that's what your teacher did. And you will also notice this is a very exothermic reaction. It released a lot of heat. It also released hydrogen gas. That's what the fizzing was. The reactivity is most reactive at the bottom and least reactive at the top. Things at the bottom are going to have a low melting point or boiling point, and a higher melting point or boiling point at the top. Alkali metals want to lose an electron, and the ones at the bottom are most reactive because there is more shielding between the electron that they want to use and the positive nucleus in the middle. Moving over one group to group 7, we have the halogens. We are still in the non-metals, and these are going to go around as diatomic molecules, which means their formula is going to be for chlorine gas, Cl2, fluorine gas, F2, bromine gas, Br2. They're going to go around together in pairs. Because they only want to gain one electron, a nice easy way for them to do that is sharing an electron with something else that is the same. So fluorine here can easily gain an extra electron by sharing it with another fluorine. They are highly reactive because they only want to gain one electron. And the most reactive ones are going to be at the top. Boiling point is going to change as we move down the group. So things are going to have a low boiling point or a low melting point are going to be at the top. High boiling points or high melting points are going to be at the bottom. When they react, they're going to gain an electron. Meaning they're going to form -1 ions. And gaining an electron is a reduction. They're going to react violently and rapidly with group 1 metals because group 1 metals want to lose 1 electrons. For example, sodium, which is a soft grey metal, will react very violently, very readily with chlorine, which is a yellow gas, to form sodium chloride, which is a white powder or salt. A more reactive element will displace a less reactive element. So here we have sodium iodide reactive with bromine. Iodine is here below bromine on the periodic table, so bromine is more reactive, so it will displace iodine in the compound, forming sodium bromide and iodine. Whereas if you try and react bromine gas with sodium chloride, chlorine is higher than bromine on the periodic table, so it's more reactive. You are going to get no reaction because bromine cannot displace chlorine out of this. These are commonly known as displacement reactions. The halogens are mostly used for sterilising things. For example, chlorine, you're commonly going to know that as from swimming pools. Halogens want to gain one electron, so the most reactive ones are at the top. That's where there's least shielding between the electron they want to gain and the nucleus. In an experiment, when you see bubbles coming off something, chances are it's going to be one of these 4 types of gases: hydrogen gas, oxygen gas, carbon dioxide, or chlorine gas. To test for hydrogen gas, it is a squeaky pop. To test for oxygen gas, it is going to relight a glowing splint. Carbon dioxide turns lime water cloudy, and chlorine gas is going to bleach damp litmus paper. When we are working out concentration, that is going to be your amount divided by your volume. Concentration is measured in moles per decimeter cubed. Amount is in moles and your volume is in decimeter cubed. To carry out a titration, first of all you need to put 25 centimeters cubed in an alkali into a conical flask, add a phenolphthalein indicator or an indicator like methyl orange, fill a burette with an acid of a known concentration, take the initial reading on the burette and record it, and while swirling the flask use the tap to slowly add drop by drop the acid into the alkali. When the first permanent colour change happens, pink to clear for phenolphthalein, stop adding the acid. Record the final volume in the burette and repeat titers until you get it within 0.05 centimeters cubed. For titration calculations, we first need to calculate the number of moles of acid used. We can use this to find the number of hydrogen ions involved in the reaction. This is going to be equal to the number of hydroxide ions at the point of neutralization. We can use this to calculate the number of moles of alkali used and concentrate the calculation of the acid. We have 25 centimeters cubed of alkali was neutralized by 15 centimeters cubed of 0.2 moles acid. Find the concentration of the alkali. First thing I'm going to do is pull all the information out of the question. Concentration of the alkali is what we're trying to find. Volume of the alkali, 25 centimeters cubed. Concentration of the acid, 0.2 moles per decimeter cubed. Volume of the acid, 15 centimeters cubed. So the first thing we do is to calculate the number of moles of acid used. So for the number of moles of acid used, we're going to use concentration of the acid times volume of the acid. That is 0.2 times the volume of the acid, which is 15, divided by 1,000 because we need it in decimeters cubed. So 0.2 times 0.015, giving us an answer of 0.003 moles. If we look at our balanced equation, we can see that acid and alkali are in a 1-to-1 ratio in this equation. So there's going to be an equal number of hydrogen and hydroxide ions. So we know that our moles of acid are 0.003 moles, which means our moles of alkali must also be 0.003 moles. Now we know the number of moles of alkali. We can use concentration by volume again, rearranging that because we know the moles and we know the volume to find the concentration. We can use moles equals concentration times volume again and rearranging that because we know our moles and we know our volume. So moles divided by volume will give us concentration. So our moles from we've just worked out is 0.003. Our concentration is 25 centimeters cubed, divided that by 1,000 to get it in decimeters cubed. So that is going to be 0.003 divided by 0.025, giving us 0.12 moles per decimeter cubed as our concentration of alkali. When you are dealing with gases, what you need to remember is that 1 mole is always going to take up 24 decimeters cubed. To work out percentage yield, you need to take your actual yields and divide it by your theoretical yields. So if this is your actual yields, then your theoretical yield is how much you thought you were going to make. To work out your atom economy, that is your MR of atoms in the required products over your MR of reactants, or the MR of stuff you wanted over the MR of the stuff you actually got. There is loads and loads of maths in this. The majority of the content of this topic and a few other bits that come out elsewhere. You can get loads and loads of practice for this in my book, Maths, the chemistry bits. It has 60 equations for you to practice balancing, loads of titration calculations, loads of bond density calculations which come up later in the course, lots and lots of things for you to do. You can measure the mass or volume of reactant or product by collecting the product, say in a gas syringe, or using a scale or balance to look at how the mass changes as a reaction progresses. There are a range of different ways you can follow a reaction. For example, you can look at the loss of mass. This would be good if you are adding something solid, like marble chips, into a liquid, and you knew that a gas was going to be produced. The gas will just go off here through the cotton wool and out, and the mass will go down. It would also, for this same reaction, if you had a solid and you're adding it into liquid and a gas was being produced, you could collect the gas either in a measuring syringe or an inverted measuring cylinder. When we are measuring the rate of a reaction, we need to look carefully at the units used. For example, here we have volume in centimetres cubed over time in minutes. So here it would be centimetres cubed per minute. And the second one, we have time in seconds and mass in grams. So this would be grams per second. In the first graph, it is volume of carbon dioxide being produced, so you can see that is going up. And in the second graph, it is mass being lost, so you can see that is going down. If you want to find the rate at a particular point, say 2 minutes or 5 minutes, you need to draw a tangent, which is a straight line, that touches the curve just at that point, not at any other point, just at the point you're interested in. And then you need to work out the gradient of that line. To work out the gradient, you need to draw a triangle. Bigger triangle, the better. And we need to work out the change in up divided by the change in across. And your units you need to take from the graph. You can compare the rates of reaction at different points in a reaction. For example, at the start of this reaction, our tangent is very, very steep. Whereas later on in the reaction, at a different point, our tangent is very, very shallow. Different rates of reaction at different points. We can follow the rate of reaction by looking at the colour change taking place in a reaction, or how it changes from clear, colourless to opaque, where we can't see across underneath it anymore. This reaction is between sodium thiosulfate and hydrochloric acid, and you need to be really, really careful with this one. Careful that when you're doing this, you're constantly washing things out so you're not contaminating things. Careful that you don't take it above 60 degrees, because then nasty gases will start to come off at the end. And careful that you don't get it on your hands, because it's going to start to irritate your hands. So with this one, health and safety is a really big concern. You can see as the reaction is going on, the cross, which was visible at the beginning, is becoming less and less visible. You need to make sure that the same person always measures the rate of reaction here. So differences in people's eyes don't mean that the differences in the type of time that the cross disappears that affect the results. One way that we can collect gas is by using an inverted measuring cylinder and putting a delivery tube through there. One of the things you need to be careful about is this gas in here that is already in the measuring cylinder before you start the experiment. That is one place that errors can be introduced. The gas is going to move from the conical flask through the delivery tube and into the measuring cylinder, and it's going to be collected and we can measure it. Adding in large marble chips now, you can see that the bubbles are starting to collect in the measuring cylinder. In this, not only can you get errors because there's going to be gas in the measuring cylinder before you start, but there is also going to be some gas lost before you manage to get the bung on. Adding in powdered calcium carbonate now, you'll notice that the rate of reaction, the bubbles are produced much, much faster, and the measuring cylinder fills up very, very quickly. When we have particles moving around at a low temperature, they're moving slowly with not much energy. When two collide, they hit each other and have a reaction, but sometimes they're going to collide and there's not going to be a reaction. When particles move around with high temperature, at high speed, with lots of energy, when things collide, you are going to get a lot of reactions taking place. Rate of reaction is going to be affected by temperature. Here I have put sugar cubes into hot water and cold water, and you can see the sugar cubes in hot water dissolved much, much faster than the sugar cubes in cold water. When we have a lump of something, it has less surface area, so there is less space to react. Here the blue dots, whatever that is, can only react with the pink dots on the outside. The purple dots in the inside are exactly the same thing, they're just not available to react. Whereas here, the pink dots are all spread out in a powder format, so they're all available to react. This is really confusing because the lump of whatever it is larger than the powder. But assuming we have exactly the same mass, the powder has more surface area than the lump, so more particles are available to react. For the rate of reaction, we can say that the higher the temperature, the faster the rate of reaction will be. This is because the particles have more energy. So they can move around faster. And this will lead to more frequent successful collisions. Here I have two identically sized blobs of glue, and one I've spread out and one I haven't spread out. I've just left it as a blob. And you see the one that's spread out, the one that has a large surface area, dries much, much faster than the blob I've just left in a big blob. I have a WhatsApp group of all my YouTube friends, and they were super, super jealous when I told them I was making a video of glue drying. we can say that the larger the surface area, the faster the rate of reaction, this is because there are more particles available to react, leading to more successful collisions. If we have things at a high pressure or at a high concentration, there are more of them, which means they're much more likely to bump into each other and react. Whereas at a low concentration, they're not very likely to bump into each other and react. We can say that the higher the pressure or concentration, the faster the rate of reaction will be, this is because there are more particles in a fixed volume, so there is a higher chance of a successful collision. When we have a catalyst, it's something that makes a reaction easier to happen. It lowers the activation energy. So for example, this catalyst fixes one of the reactants in place so that it's easy for the other reactant to find it. Whereas over this side, they're both randomly wandering around in the dark, and it's quite hard to find people when you're randomly wandering around in the dark. Excellent work so far, guys. Well done. Only a little bit longer. Let's keep going. Tiny mental break, and then we can keep going. This half arrow on top of the other half arrow going in the opposite direction is a symbol for a reversible reaction. Ammonium chloride will decompose into ammonia and hydrogen chloride gas upon heating, and this is an endothermic reaction because you need to put heat into it. Cooling it is an exothermic reaction because energy will come out. Hydrated copper sulfate, which is the lovely blue colour, upon heating will lose the water, turn into anhydrous copper sulfate, which is a white colour. Adding water in will turn it back to hydrated copper sulfate. Le Chatelier's principle tells us that whatever you do to a reversible reaction, the reaction will do the opposite. So in this reaction, this way is endothermic and this way is exothermic. So if you heat up a reaction, the endothermic reaction will increase to compensate, and the exothermic reaction will decrease to compensate. Whereas if you decrease the temperature, then the endothermic reaction will decrease to compensate, and the exothermic reaction will increase to compensate, so that the overall temperature stays the same. If you're going to change the temperature or the concentration, the reaction will also adjust itself to compensate. If you are going to increase the pressure or the concentration, then the reaction will shift to the side that has less moles to compensate. If you're going to decrease, then it will shift to the side that has more moles to compensate. We can list the metals by how reactive they are, with the most reactive being at the top and the least reactive being at the bottom. Now you need to remember these. If you have any good mnemonics remembering these, you can pop these in the description below, in the comments below. That would really, really help other people. Things that are above carbon need electrolysis to be extracted, whereas things that are below carbon can just be extracted by reduction. However, things that are really, really unreactive, like silver, gold and copper, are generally found in the earth as their pure ores, unreacted with anything. Everything else is generally going to be reacted with oxygen in the form of metal oxides. You can also use this to predict the products from electrolysis. If the metal you are used in the electrolysis is more reactive than hydrogen, then you're going to get hydrogen as a gas. If it is less reactive, then you're going to get something else as a gas. And we can use this to predict the products for displacement reactions. If we reacted magnesium chloride with calcium, because calcium is more reactive than the magnesium, the calcium is going to take the place. So we are going to get calcium chloride plus magnesium as our products. However, if we reacted magnesium chloride with aluminium, because magnesium is more reactive, aluminium cannot take the place, it will not displace it, so no reaction is going to take place. Aluminium electrolysis is a slightly different form of electrolysis. We have one electrode up here, this is our positive anode, and another electrode down here, this is our negative cathode. The molten aluminium and the cryolite. Cryolite is just a compound that is added to reduce the melting point of molten aluminium oxide. It's added into this reaction vessel and we get one reaction taking place down here and another reaction taking place at the top. At the bottom, at the negative cathode, we are going to be attracting the positive aluminium ions. They are going to be picking up electrons and turning into aluminium atoms. This is 3+, so it needs to pick up 3 electrons. And then at the top, at the carbon electrode, we are going to attract the negative oxygens. They are going to be losing electrons and turning into oxygen gas. Because we have 2 on this side, 2 oxygens on that side, we need 2 on that side, which means we now have 4 negative charges, so we need to lose 4 electrons as well. This is a carbon electrode up here, and we are starting a reaction which causes oxygen gas to be evolved. Eventually, the oxygen gas will react with the carbon electrode, and we are going to lose the electrode as carbon dioxide. So the carbon dioxide will wear away the electrode eventually, so this will need to be replaced. The molten aluminium collects at the bottom and can be taken off like that, and that is how we purify aluminium. There are lots of very important metals on Earth, and some of them are very, very rare. So we need to develop new ways to get rare metals out of low yield ores. Low yield is where using traditional mining methods wouldn't be financially viable. 2 of these methods are bioleaching and phytomining. Bioleaching is when we have a large body of water, say a lake, which has metal in it, such as copper dissolved in it. If we want to get the copper out of the lake, out of the water, we can add in bacteria. These will take up the copper from the water and then they will leach out copper ions. It's basically the bacteria's way. Another method is if we have lots of copper again in the soil but at very, very low yield. So not enough for us to dig up the soil and get the copper out, say by reduction or electrolysis. We can put plants in. This is generally, believe it or not, broccoli. The plants will then absorb the copper ions from the soil. We can then cut them down and burn them, and then from the ash we can do electrolysis. The disadvantage of using phytomining is that plants grow very slowly. Ammonium sulfate can be made from the reaction of ammonia and sulfuric acid, or ammonium hydroxide and sulfuric acid. Fertilisers are good because they increase crop production, but they also lead to an increase in eutrophication. When you're doing a life cycle assessment of an object, you need to look at the different stages of its life: the manufacture, the use, and the disposal, and the environmental impacts of each of these sections. So the environmental impacts of the energy, so the energy needed for production of this, bearing in mind that this generally comes from fossil fuels which have been burnt, so electricity based on fossil fuels, leading to carbon dioxide being put into the atmosphere. The materials used, whether they can be used from natural resources or whether something else can be used, whether natural resources have to be further processed, the production of the product, using the product, and disposal of the product. Using the product, does it need electricity to use it? Does anything come out of it when it's being used? Production of the product, we're talking about things like atom economy, how much of the reactants are actually going to end up in the product, how much waste is there, how much waste of the natural resources that went into it when you're making the product, and disposal of the product. Can it be recycled? Can it be incinerated for another use, or is it just going to have to go to landfill? Thermosetting and thermosoftening polymers have very, very different properties, and this is based on their structures. Both have long polymer chains in, but thermosetting have crosslinks, whereas thermosoftening don't have crosslinks. This means upon heating, the thermosoftening polymers can just slide past each other, whereas the thermosetting polymers cannot slide past each other. Which means thermosetting polymers are going to burn and thermosoftening polymers are going to melt. The word mono means one, and mer means bit. Poly means lots, and mer means bits. So we can say that a monomer is one bit and a polymer is lots of bits that have all been put together. A couple of key definitions you need to know. A hydrocarbon is a compound that is made up of hydrogen and carbon only and nothing else. Crude oil is a mixture of different length hydrocarbons. To separate out the mixture of crude oil, we need to use fractional distillation. Crude oil goes in, gets heated up until it is a gas. It then goes into a condensing column. All of the really, really long chain hydrocarbons, which don't evaporate, come off here as a residue, and we can use that, the bitumen, we can use that for making roads. It is very, very hot at the bottom, and as we move up the condensing tower, the temperature goes down. And at each different point, different length hydrocarbons are going to come off. So we have gases at the top, petrol, naphtha, kerosene, which is fuel for planes, diesel, and then fuel for boats. Short hydrocarbons are going to come off at the top, and long hydrocarbons are going to come off at the bottom. Things at the top are going to be really, really flammable. Things at the bottom aren't going to be really, really flammable. Things at the bottom are going to be really viscous, whereas things at the top aren't going to be viscous. The long hydrocarbons that come out of fractional distillation aren't always the most useful ones. We get large amounts of the long ones which aren't very useful, but we don't get very many short ones which we need because they are useful. So we can crack the long ones using heat and a catalyst. And this is going to give us short alkanes, which we want, and alkenes. The air we breathe is made up of lots of different gases, predominantly nitrogen gas with about 20-21% oxygen in there, and then lots of other gases, including a small amount of carbon dioxide. This is very different to the early atmosphere, which is mainly formed by things coming out of volcanoes. So we had a large amount of ammonia, methane, water vapour up in the air, carbon dioxide. This would have been a pretty unpleasant place to be. Ammonia smells like, well, it's a hair dye or like really, really old baby nappies. And methane smells like farts. So the early atmosphere, the early Earth, would have smelt like farts and weak old baby nappies. The level of water vapour in the atmosphere decreased as it rained, which made the oceans. The levels of carbon dioxide decreased as the carbon dioxide dissolved in the newly formed oceans. It turned into fossils, became locked up in rocks, and photosynthesis started to take place. With the evolution of green plants, oxygen started to increase as the photosynthesis was taking place. There are three main greenhouse gases, with the biggest culprit being carbon dioxide and to a much smaller extent water vapour and methane. The bonds in carbon dioxide are really, really good at absorbing infrared or heat radiation, which traps it inside our atmosphere and warms the planet. Which means that when heat, light, energy from the sun comes to us, it will be reflected back by the Earth, and normally this would go straight back out into space, but it's not. It's being trapped by the greenhouse gases, by the carbon dioxide, by the methane, which means it stays in our atmosphere, heating it up. We can see a gradual increase in the levels of carbon dioxide, which has taken up speed in recent years. And there are lots of things that humans do that have a massive amount of the levels of carbon dioxide in their atmosphere. Global warming is a slightly confusing term because not everywhere is getting hotter. While we do have places where they're getting hotter, where deserts, countries, farmland is drying out completely, and the ice poles are getting hotter as well, which is really, really bad for the polar bears. Because they live on these blocks of ice. They hunt in the water, and when they need a break from swimming and hunting, they jump onto the blocks of ice and have a rest. The problem is, if these blocks of ice are melting, there is nowhere for the polar bears to have a rest, so loads and loads of polar bears are drowning. And while the ice caps are melting, it means we are seeing increased levels of flooding in other places. As the sea levels go up, certain places, starting with places on the coast, are going to start to end up underwater. While Australia is having its hottest Christmases ever, us here in the UK are having our coldest Christmases ever, seeing unprecedented levels of snow. And the climate change doesn't just affect people, it affects animals and plants as well. As the temperature changes, the top of the mountain, which perhaps used to be under snow, is now available for habitation by new animals and plants. Now, say if you had a little house here and you knew it was protected from certain types of animals because it was too cold or too warm for them there. With a changing climate, animals are moving up and down slopes, their habitats are changing as the temperature changes and as the location of their food source changes. Your carbon footprint is how much carbon your daily activities contribute to the atmosphere. This is going to be impacted by things such as whether you decide to drive or whether you walk to your location, and whether you decide to eat food that is grown locally or food that has had to travel a long distance. Lots of human activities contribute to the production of carbon dioxide. Burning fossil fuels for use as electricity, deforestation, cutting down trees so that the trees can't take up carbon dioxide from the atmosphere anymore, and our reliance on petrol cars. The predictions for the levels of carbon dioxide in the atmosphere is that they are just going to increase, and global warming is going to increase as well, unless we as a population decide to do something about it. One of the major pollutants is sulfur dioxide. When this goes up into the atmosphere, dissolves in the clouds, it is going to come back down as acid rain. This is going to have an effect on a wide range of things. It is going to hurt the animals that come into contact with it if a lake or an ocean or a pond becomes too acidic. That's going to start to kill the fish and the plants in there. Plants are not going to appreciate having acid rained on them, so they're going to die, and it is also going to destroy limestone statues which are going to dissolve in the acid rain. Too much carbon in the air is going to lead to large levels of smog and global dimming. This is particularly prevalent in developing countries. When I was in Beijing, it was really hard to see out the window because it was so smoggy. Water vapour is going to contribute to the warming of the planet. Carbon monoxide is a toxic gas, and nitrogen oxides are going to contribute to both smog and acid rain. We would not survive very long without water. But only a small percent of the water on Earth is suitable for us to drink, so we need to remove salts from it, which is desalination, and we need to make it safe to drink, or portable water. To make water safe to drink, we need to remove any dirt, mud in there, so any large solids. We need to remove the bacteria, and we need to remove any nasty or unwanted bits of too many mineral ions, like the salt that would be in seawater. We add in various different things to water. We add in chlorine to kill things, and we add in fluoride for tooth protection and bone protection. Well done, you little superstars. Fantastic work. The rest of this video is for chemistry only. So some of you can go and have a rest now, some of you still have a bit more work to do. The big chunk in the middle are the transition metals. Transition metals are in the middle. Their properties are that they are hard, shiny, and are good conductors. These are basically your traditional metals, so any property of traditional metal, you can generally associate it with a transition metal. Because of their properties, they can be used in jewellery, in wires, or in saucepans. And because they get all these different colours, they can be used for things like stained glass or for coating statues. Here the Statue of Liberty has a copper coating. Copper, transition metal compounds are generally going to be blue or a bluey green. Iron 2 is light green. Iron 3 is an orangey brown, a rust colour. And cobalt is a really lovely deep rich blue. If you're going to use sodium hydroxide to test for your positive ions, we need to look at the ionic equations and we need to look at the precipitates. Testing for aluminium with sodium hydroxide is going to give you a white precipitate, which is then going to dissolve. Testing for calcium with sodium hydroxide is just going to give you a white precipitate, which will not dissolve. Testing for magnesium with sodium hydroxide will give you a white precipitate, so in this circumstance you would need another test to differentiate between calcium and magnesium. Copper ions will give you a light blue precipitate, iron 2 ions will give you a grey-green precipitate, and iron 3 ions will give you an orange precipitate. For the ionic equations, we have our hydroxide ion and then our metal ions, and you are expected to know all of these. Then you just need to make sure your number of negative hydroxide ions is equal to the number of positive ions. So aluminium is 3 positive, so it needs 3 negative ions to become neutral overall. Calcium is 2 positive, so it needs 2 negative ions to become neutral overall. Magnesium, OH2, calcium, OH2, iron, OH2, iron 3, OH3. If you want to test something for a carbonate ion, you need to add hydrochloric acid, set up a delivery tube so any gas evolved will be collected down into lime water, and if it's carbon dioxide, the lime water will go cloudy. If you want to test a sample to see if it contains sulfite ions, you need to add hydrochloric acid, you need to add barium chloride, and if it contains sulfite ions, you will get a white precipitate formed. If you want to test for halide ions, you can add silver nitrate, and chloride ions will give a white precipitate. Bromide ions will give a cream precipitate, and iodide ions will give a yellow precipitate. Yellow, but not as yellow as the walls of my lab used to be. Now this can sometimes be a very, very subtle difference, and the best way to do it is by comparing it with the other things. I love flame tests. They are so, so pretty. You need to know that lithium will burn with the crimson flame, sodium will burn with the yellow flame, potassium will burn with the lilac flame, calcium with the red flame, barium with the green flame, even though it doesn't look green, and copper is going to burn with the blue-green flame. In some cases, doing tests in class might not be as good as using an instrumental method. Instrumental methods can be faster, they can be more accurate, and they are unbiased. The Haber process produces ammonia from nitrogen and hydrogen gas. Our main source of nitrogen and hydrogen gas is getting them from the air. We can also get hydrogen gas from the electrolysis of water. They are fed into the reaction vessel where they'll be turned into ammonia, which is a liquid, so that can be taken off at the bottom. And any unreacted gases can go back round into the reaction. It is done at 450 degrees C at 200 atmospheres and using an iron catalyst. The production of ammonia is very important because it is an important source of nitrogen for fertilisers. The conditions used in the Haber process are actually a compromise. The forward reaction is exothermic, so this tells us, using Le Chatelier's principle of dynamic equilibrium, that we should be using a low temperature if we want to drive the forward reaction. But at a low temperature, we have a low rate of reaction. So even though using the high temperature of 450 degrees drives the backwards reaction away from ammonia towards the production of the gas, the rate of reaction is so fast that it is constantly cycling between the two. So 450 degrees is a compromised temperature. The ammonia comes off as a liquid, so that can be taken off, that can be removed, which is also going to drive the forward reaction. There are less moles of product than there are moles of reactant. There are 4 over this side and 2 over this side. So high pressures of 200 atmospheres are going to drive the forward reaction because this is going to take up less space. There are less moles of it. A higher pressure would increase the rate of the forward reaction even more, but it would be dangerous because high pressure leads to risk of explosion. So 200 atmospheres is used because it is a relatively safe pressure to do it with. As we increase the pressure, the danger to the workers increases, the thickness of the walls increases, and also stuff like insurance costs are going to increase. Metals are made up of positive atoms in a sea of delocalized electrons, and these electrons being free to move is the reason that metal can conduct electricity and why it's so good at conducting heat. An alloy looks slightly different to a metal. We still have our positive ions, we still have our delocalized electrons, but there's something else in there as well. This may be another metal it's alloyed with, or it may be something else like carbon that it's alloyed with. Pure metals have layers. Layers can slide across each other. Because they have layers and because they can slide across each other, they are soft. Alloys don't have layers, or they have distorted layers. And the distorted layers cannot slide. And because the distorted layers cannot slide, it means they are hard. For rusting to take place, we need to have iron, oxygen, and water, and that is going to result in iron oxide. You can see in my experiment here that the iron oxide is this brown, orangey red stuff that is on the sides. Rusting will actually lead to an increase in mass because you're taking the iron and you're adding in the oxygen. There are a couple of ways we can stop this from happening. We can galvanize things. We can coat things. We can use a sacrificial metal. The majority of glass we use is made up from silicon dioxide. Ceramics, such as clay ceramics, are a mixture of silicon dioxide and aluminium oxide. Alkanes are hydrocarbons with single bonds only, and the general formula for them is CnH2n plus 2. The first one with one carbon is methane, 2 carbons is ethane, 3 carbons is propane, and 4 carbons is butane. When we're drawing organic compounds, the important thing to remember is that hydrogen always makes one bond and one bond only, and carbon always makes 4 bonds and 4 bonds only. So you can see when I've drawn them, each of the hydrogens here only ever makes one bond, whereas the carbons each make 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. And because these are alkanes, they're only ever going to have single bonds. This line here represents a bond, and that is a pair of electrons. This is a covalent bond between these. You need to know the names and be able to recognise the pictures of these. And we can see the formula for these follows our general formula of CnH2n plus 2. So methane has 1 carbon and 4 hydrogens, ethane 2 carbons, 6 hydrogens, propane 3 carbons, 8 hydrogens, and butane 4 carbons and 10 hydrogens. The complete combustion of a hydrocarbon involves lots of oxygen. That is your roaring blue flame on a Bunsen burner. This is going to be hydrocarbon plus oxygen turns into water and carbon dioxide. Incomplete combustion is where there's not enough oxygen. This is going to be your orange flame on a Bunsen burner. This is much more problematic because as well as the water and carbon dioxide, we're going to get carbon monoxide, which is highly toxic. Your white blood cells prefer it to oxygen, so you will actually suffocate to death, generally in your sleep, and carbon, which is black soot, which gets everywhere. Alkenes have a double bond and are unsaturated. The general formula for them is CnH2n. All of these are going to end in -ene, so there is, with 2 carbons, ethene with 3 carbons, propene with 4 carbons, butene with 5 carbons, pentene. When we're drawing things in organic chemistry, we need to remember that hydrogen always makes 1 bond and carbon always makes 4 bonds. So ethene down here, hydrogen is making 1 bond and our carbon is making 1, 2, 3, 4 bonds. This second carbon is making 1, 2, 3, 4 bonds. A bond is a pair of electrons that are covalently shared. So a bond can be used by more than one carbon or hydrogen when we're counting things. You need to be careful looking at these ones, 1, 2, 3, 4. It would be very easy to make a mistake drawing some of the carbons in the middle here. You need to know how to name, recognise and draw the first 4 alkenes. The formulas for these: for ethene, C2H4, propane, C3H6, butene, C4H8, pentene, C5H10. You need to know how to test for alkenes. This is also the test for double bonds or unsaturation. You can see alkenes have 2 E's in there. It means they have double bonds. For this test we use bromine water and it goes from orange to colourless. Colourless is really, really important here. Clear is not going to be enough to get you the marks, it has to be colourless. To make this slightly harder, the examiners might throw in some isomers. So this double bond for butene doesn't need to be here, it could be here. And these are named differently. Here the double bond is in carbon number 1, so that is but1ene. Here the double bond is in carbon number 1, 2, so this is but2ene. Here the double bond is in carbon number 1, so this is pent1ene, whereas here the double bond is in carbon number 2, so this is pent2ene. If we're going to have a monomer of ethene, that will just become polyethene, so just putting poly in front of the name there. And if we want to take the drawing and turn it into a polymer, we need to take this double bond and break it. So that bond goes outside. We have a single bond between our two carbons. That's the other half of the bond. Drawing in our hydrogens. Square brackets. You need to make sure your bond extends outside the square brackets, and a little N after it. And then you need to have a big N in front of your monomer. If you want to have a polymer of propene, we're going to turn that into polypropene. We need to draw it in a slightly different way to the way you may be used to drawing it, with our double bond here and our third carbon up here going round a corner. Exactly the same way. Break one of the bonds, one bond left in the middle, other bond goes outside, and then all of the other groups around the hydrogen stay the same. Little N after it, big N in front of it. If they want to try and make this more complicated, they could change this CH3 group to a fluorine group or a bromine group. All you'd do then is exactly the same, just replace the fluorine group in the same place. Alcohols have an OH functional group and they end in ol. So one with one carbon is going to be methanol. With two carbons, ethanol. With three carbons, propanol. With four carbons, butanol. When we draw our alcohols, we need to put our OH groups on here. And we need to remember and make sure everything has the right number of bonds. Hydrogen is only ever going to make one bond, carbon makes four bonds, and oxygen makes two bonds. Organic chemistry is a very likely place for them to sneak nasty questions in, and this is one of the nasty questions they could sneak in. Propan 1-ol has our alcohol group right on the end. Butan 1-ol has our alcohol group right on the ends. Propan 2-ol has it in the middle. Here is our alcohol group up here, and butan 2-ol has it in the middle here. Learn these and recognise them. Another way of producing alcohol is fermentation. This is where we take sugar, we mix it with yeast, we keep it nice and warm, and we're going to get ethanol, which you can use for alcohol, or carbon dioxide, which makes the bubbles in bread. Exactly the same process beer making and bread making. Alcohol can be used for drinking or as a solvent. When you react it with sodium, it's going to fizz. When you react with oxygen, it's going to burn. It's just combustion reaction. And when you react it with water, it's going to dissolve. Carboxylic acids have this as a functional group. Something with one carbon is methanoic acid. Two carbons is ethanoic acid. Three carbons, propanoic acid. Four carbons, butanoic acid. Methanoic acid, one carbon making four bonds, double bonded to oxygen and an alcohol group. Ethanoic acid, propanoic acid and butanoic acid. You need to be able to recognise and draw these. You use carboxylic acid to much more than you recognise because ethanoic acid is vinegar. It is an acid, so if you react with any carbonate, you're going to get your standard acid carbonate reaction and it's going to fizz. And if you react with alcohols, you're going to make an ester. If you react an alcohol with carboxylic acid, you're going to get an ester. For example, if you react ethanol with ethanoic acid, you're going to get ethyl, ethanoate, and water. When we polymerise something, and this is I'm going to show you is condensation polymerisation, we add monomers together. In condensation polymerisation, we're going to add these bits together here, and we're going to lose a water molecule. For condensation polymerisation, you can see we had two different functional groups here. The opposite ends of amino acids, which I've drawn here, and we have lost water as a small molecule. Condensation polymerisation is when we lose a small molecule from the reaction, and it is usually water, but not always. Here is the structure of DNA that I have sitting on my desk, and you can see that there are two lines going through it, because DNA is double helix structure. You can see each of the bases in here all the different colours. The bases are A, T, C and G, and they go together in that format. A always bonds with T, C always bonds with G. This is to do with the number of connections they can make. So you're always going to get A bonding with T and C bonding with G. It has a sugar phosphate backbone. And there are two of these that go up the side around the DNA. Two strands that can break apart down the middle when the DNA wants to replicate. A section of DNA, such as this, can be called a gene, and then genes hold the information for making amino acids and proteins, which are the building block of you and me. Sections of DNA can be read, so 3 bases of DNA can be read and turned into an amino acid. These amino acids can then build all together to make a gene. Here we have a simple cell with 2 different metals, copper and zinc, in their own solution. So here is zinc in zinc sulfate solution and copper in copper sulfate solution. They are connected by a salt bridge or an ion bridge, and because zinc is higher in the electrochemical series, it is going to push electrons this way towards copper. A flow of electrons means we are going to have a potential difference. So the zinc is going to be giving up electrons and the copper is going to be accepting electrons. That thing that we commonly refer to as a battery is actually a cell. I know it's really annoying. A cell is one battery. A battery is more than one cells. So this is a cell, and then 2 or more of them together would be a battery. In non-rechargeable batteries, the chemical reaction that produces electricity, once that is used up, the battery is dead. Whereas in a rechargeable battery, there is a reversible reaction that goes on. So once the reactants are used up, you can pass electricity through it, which will cause the reaction to go in the opposite direction, recharging the battery. In a hydrogen fuel cell, we just have hydrogen gas reacting with oxygen gas and turning into water. There is a large amount of energy released. Which can be used to power an electric car. And water is the only product which means there are no carbon emissions. There are a few problems with this, predominantly with the production of hydrogen. At the moment this uses fossil fuels because hydrogen can either be made by reacting steam with coal or natural gas, which are both fossil fuels, or hydrogen is made by electrolysis of water, but that involves electricity which is generated using fossil fuels. The other problems are it's quite hard to find. The hydrogen needs to be compressed. Which is a problem because it will be explosive. It also needs a very, very large tank to store it in. And they don't work at low temperatures. At the negative electrode, we are going to have hydrogen gas minus 2 electrons turning into hydrogen ions. At the positive electrode, we are going to have these hydrogen ions reacting with the oxygen gas and some electrons, and they are then going to turn into the water. Ouch! This is why in some videos I have unexplained scratches.